d theta. Okay? But now what do I do with that? Well, first I said A is constant, so dA is 0. Second, well, actually we don't like B at all, right? We want to view A as a function of theta. So, well, maybe we actually want to use this formula for dB that we found in here. Okay, and then we'll be left only with d thetas, which is what we want. So if we plug this one into that one, we get dA equals 1/2 A sine theta times B tangent theta d theta plus 1/2 AB cosine theta d theta. And if we collect these things together, we get 1/2 of AB times sine theta times tangent theta plus cosine theta d theta. And if you know your trig, then you will see that this is sine square over cosine plus cosine square over cosine. That's the same as secant theta. So now you have expressed dA as something times d theta. Well, that coefficient is the rate of change of A with respect to theta, with the understanding that we are keeping A fixed and letting B vary as a dependent variable. Not enough space, sorry. Okay, in case it's clearer for you, let's think about it backwards. So we wanted to find how A changes. To find how A changes, we write dA. But now this tells us how A depends on little a, little b, and theta. Well, we know actually we want to keep little a constant, so we set this to be 0. Theta, well, we're very happy because we want to express things in terms of theta. dB, we want to get rid of. How do we get rid of dB? Well, we do that by figuring out how B depends on theta when A is fixed. And we do that by differentiating the constraint equation and setting dA equal to 0. Okay, so I guess to summarize the method, we wrote dA in terms of dA, dB, d theta. Then we say that A is constant, means we set dA equals 0. And the third thing is that because, well, we differentiate the constraint, and we can solve for dB in terms of d theta. And then we plug into dA, and we get the answer. Okay. Oops. So here's another method to do the same thing differently. It's to use the chain rule. So we can use the chain rule with dependent variables. Okay? So what does the chain rule tell us? The chain rule tells us, so we will want to differentiate the formula for A with respect to theta holding A constant. So I claim, well, what does the chain rule tell us? It tells us that, well, when we change things, A changes because of the changes in the variables. So part of it is that A depends on theta, and theta changes. How fast does theta change? Well, you could call that the rate of change of theta with respect to theta with A constant. But of course, how fast does theta depend on itself? The answer is 1. So that's pretty easy. Plus, then we have this, the partial derivative, the formal partial derivative of A with respect to little a times the rate of change of A in our situation. Well, how does little a change if A is constant? Well, it doesn't change. And then there's A sub little b, the formal partial derivative, times, the rate of change of B. Okay, and how do we find this one? Well, here we have to use the constraint. Okay, and we can find this one from the constraint, as we've seen at the beginning, either by differentiating the constraint or by using the chain rule on the constraint. So, of course, the calculations are exactly the same. See, this is the same formula as the one over there, just dividing everything by partial theta and with subscript little a. But if if it's easier for you to think about it this way, then that's also valid. Okay, so tomorrow we are going to review for the test. So I'm going to tell you a bit more about this also as we go over one practice problem on that.